Hello, so today I'll be going through an equilibrium question and a chemical bonding question. So let us first take a look at the equilibrium question. So we are focusing now on this chemical equilibrium over here. This one right here. And so in a study of this decomposition, 2 moles of disulfur dechlorfluoride was placed in a 2 dm³ flask and heated up to 100 degrees Celsius. Concentration became 0.5 mole per dm³ at equilibrium. So calculate the value of Kc at 100 degrees Celsius, including the units. So initially, what is the concentration at S2F10? You will agree will be 2 moles divided by 2 dm³ will give you 1 mole per dm³. So that's the initial concentration of S2F10. And then we can construct an ice table in terms of concentration. So we know that eventually it's concentrated at 0.50. So it must have lost, there must be a decrease of 0.50 mole per dm³. Consequently, the concentration of the products must also be 0.50 mole per dm³. Substituting the values into the Kc expression, we get a Kc value of 0.50 mole per dm³. So let us take a look at the second part, which is actually the more interesting part. So to this equilibrium mixture, a certain mass, an unknown mass of disulfur dechlorfluoride was added. New equilibrium concentration is now 2.50 mole per dm³. So we do not know what is this mass. So let the amount of disulfur dechlorfluoride be X moles. Or let the initial, or rather let the increase in concentration of disulfur dechlorfluoride be X mole per dm³, because we want to work with an ice table in mole per dm³ concentration values, right? So now the new initial concentration immediately after the addition and before the system can equilibrate is 0.50 plus X, if you agree with me. And before the system can equilibrate at this moment, the products have the same concentration of 0.50. Then there's this, some students may make the mistake of adding this plus X under change in concentration. Now this change in concentration is usually referring to the change that is a result of the system equilibrating itself. So this is separate from the man-made addition of the disulfur dechlorfluoride, which is a perturbation to the system. So the system equilibrating itself will give rise to a change in concentration of an unknown amount y, and so resulting in the eventual equilibrium concentration of 2.50 for S2F10 and 0.50 plus this unknown y for both SF4 and SF6. So now we know that it's at the same temperature, so the Kc will be the same. So you can substitute these equilibrium values into the Kc expression, thus getting this equality 0.50 plus y squared divided by 2.50 equals to 0.50. So we can just rearrange this equality to get us this expression to find y to be 0.61803. And now we got one unknown, we just need to solve for the other unknown, and we can just focus on this column to solve for the other unknown, which is 0.50 plus x minus y equals 2.50. So x must hence be 2.61803. So we know that that is the increase in concentration of S2F10. So what is the increase in mass of S2F10? Is the concentration times the volume, 2 dm³, times the mR of S2F10 will give you, wow, a very large value of 1.33 kilograms. Okay, so we are done. This is a fairly interesting equilibrium question, right? Because now there's two unknowns, so it's fairly interesting. But let us look at the slightly less exciting but also sufficiently interesting second part of the question, which is about interhalogen compounds. So okay, it's very reactive. CrF3 causes sand to explode. So they share the same molecular shape, however the FCr-F1 angle is predicted to be smaller than the BrCl-Br angle. Okay, so explain why bromine is less electronegative than fluorine. Okay, this is a standard question, so I shall write the standard answer. So from or rather bromine has one additional electronic shell than fluorine. Despite bromine's higher nuclear charge, shielding effect is much larger. Shielding effect is greater for bromine due to greater number of inner shell electrons. Hence, effective nuclear charge is smaller for bromine, and the electrostatic attraction between the nucleus, but now we're talking about electronegativity, so it's not valence electron but bonding electrons, is smaller for bromine than for fluorine. Okay, so this is a very standard question. So take note of a few key points that you need to ensure that you answer. Firstly, you need to say nuclear charge. You need to answer nuclear charge. You need to answer shielding effect. And then nuclear charge plus shielding effect gives to effective nuclear charge. And then you must talk about electrostatic attraction. And then finally, leading us to a conclusion, Br is less electronegative. Okay, so let us take a look at part 2. Hence or otherwise, explain the relative sizes of the two bond angles. So actually, they are giving you a lot of free room over here to work with, because they have option to answer hence based on part 1 or otherwise. So actually, there's two possible explanations for this question. Why the FCl-F bond angle is smaller than the BrCl-Br angle. So let us first take a look at how electronegativity can help to answer this trend. So we'll take a look at these two compounds. So you know the FCl-F bond angle is smaller. FCl-F angle is smaller than the BrCl-Br. Okay, so it's quite obvious once you start to take a look at where the lone pair of where the bond pair of electrons are. In the Cl-F bond, they are closer to the F atoms, because F is more electronegative than Cl. But in the Cl-Br bond, it's closer to the Cl atom, because Cl is more electronegative than Br. So what we notice is that the bond pairs exert greater repulsion in the Cl-Br3 molecule, because they are closer to the central atom, while they are further away from the central Cl atom in the Cl-F3 molecule. So we can write the following. Or rather, as Br is less electronegative. Okay, it's just my phrasing. How to make it more smooth in your presentation delivery. As Br is less electronegative than F, the bond pairs of electrons is closer to the central Cl atom in Cl-Br3 than in Cl-F3, exerting greater repulsion on one another, causing bond angle causing the BrCl-Br bond angle to be larger than the FCl-F bond angle. Alternatively, as the Br atom is larger than the F atom due to greater number of electronic shells, the BRCL BR bond angle is larger than the FCL F bond angle. Or rather, to make it more complete, I'll say because the Br atom is larger than F atom, the repulsion between the the electron clouds of the Br atoms is greater than the repulsion between the electron clouds of the F atoms. Hence, the BRCL BR bond angle is larger than the FCL F bond angle. Okay, so I'm done now with the solution to this question, and I will solve equally interesting question in the next video.